use kinematics model only. So pure pursuit is basically trying to just pick a point in your target trajectory that you got from your motion planner and tries to reach to that. Stanley, I'm not going to details again. Stanley is similar to pure pursuit, but instead of targeting one look ahead point, it is trying to minimize the lateral distance and also heading angle between the path, cross track error and the heading angle of the path. The PID, then comes the PID and other non-kinematic controllers. Special mention to MPC, which are being used a lot, but the MPC is basically similar to kind of going back to trajectory planning here. You have your sequence of points, look ahead points that you kind of predict using some model-based plan, and you try to optimize your sequence of controls basically that you will take. You look at the problem as not only one control value, but your sequence of control. And so steer and axle commands you're going to give. The problem becomes more smooth in some sense. A nonlinear MPC is a little bit one touch above on that. You can basically you can add a lot of nonlinear constraints on a linear MPC problem. Time is running out, so I'll jump right into the reinforcement learning. Reinforcement learning is basically a cutting edge algorithm that is basically used for, you can have end-to-end applications where you are giving image space basically from camera and then you can get the steering angle. But whereas more sophisticated, that is kind of very hard to do beyond the demo. In production, it's very, very hard to use. In production, it's only used with in conjunction with other parts of the stack, which I described here already. Mostly like you get object information and you take some from the reinforcement learning, you will get some kind of action information in terms of lane keep or lane change, or maybe steering, if you get a little bit more end-to-end like steering angle or an axle and brake pedal information from there. So what is reinforcement learning? Reinforcement learning is, when we say learning, for example, there are different kinds of learning, supervised learning and supervised learning for those who you have taken machine learning. And reinforcement learning is kind of the third kind of learning, I would say. So for a supervised learning, when we learn how to drive, somebody kind of comes and teaches us, and kind of mentions us how to drive and gives us a couple of days of training, and we learn very fast from them. But he cannot teach us everything, all the different, or maybe we can learn some of that from a rule book and all. So that is your supervised learning. Once we start driving, we as humans see basically through direct basically colliding with others, or more likely we learn from near misses and all. So that is where reinforcement learning comes. Reinforcement learning is basically you learn by running a lot of trial and errors basically, and you learn by mistakes basically. So you have an agent which is similar to a driver and who is interacting with most of the cases it's simulation environment. That's why it's very popular in, I've shown all these examples here. These are all the board games and even more complex games like Atari and Dota. Reinforcement learning is getting more used other than AVs. You basically give action like a high level action or a low level control steer action, and you get some kind of based on state you give action, and then you get the environment gives you some kind of reward. If like you reached your goal, you get a good reward, or you did a collision, you get a bad reward, something like that. And you do this infinite times, many times, and then with that you learn. Usually, I'll come to that later. Usually, with some kind of neural net, you basically learn like a policy, how to drive. So neural net, whole reinforcement learning is based on Markov decision process. Basically, the action that you should take is based on the current state only. That's the whole paradigm of Markov decision process. So the whole problem can be described by state, action, reward, transition, and probability of the next state, and a discount factor. Without going in, like, and again, like this will take more time, but in general, you have a state, and you get like while you're driving, you are looking at your state information, other actors or lane information, and you are taking some action in terms of whether you did a good driving or bad driving. That is your agent, and this is the framework. And then you train with this framework basically by doing this mostly in simulation. And then sometimes after you train the agent a lot in simulation, you can do some online feedback as well. The objective is basically to find a policy that will, given a state, it will specify what action to take. And given a state, what action to take. So policy is just a mapping basically between what you see, what a bad policy is a bad drivers. Autonomous driving system, we are trying to come up with the optimal policy, the best policy, of course. We're trying to come up with the best driver, but obviously there could be bad drivers. Part of the if you deep dive into reinforcement learning, you know that it's not always possible to know what is good without exploring what is bad. So you have to know a lot of what is bad driving to know what is good driving, kind of. That's the whole thing. So not going into too much details again. Very simple problem here I'm showing here. So here, like a board game where you get a very high reward by reaching this, no matter which state you start. This is more like your simplified chase problems, maybe. A random policy, no, there could be a bad policy also. A random policy is where you are equally likely for wherever you start, your 25% chance of going up, left, right, or down. That is your random policy. Board problem, I have given what is optimal policy. Like if you are here, your optimal policy is go left, not right. Here you go down here. That is the optimal policy. Bad policy will be obviously opposite of optimal policy. Let's say, like, if optimal policy is going left, you say right. There's some stochasticity in the policy, of course, where you are, from this point you can go left, right, or bottom. It's equally likely you'll get end up in these 2 points. That is, I'm not going to the mathematics here. I'm skipping here. A dip RL is basically what happens is, like I kind of mentioned, like what is a optimal policy in kind of a table manner. Basically, if I give this board game, like if this is 0 0, this is 0 1 cell, this is 0 2 cell, this is 1 0 cell, this is 1 1 cell, something like that. I can have a tabular representation of what is the optimal policy for each cell, basically. Deep RL takes it, abstract that in a more level. This is not a scalable, of course. Like you, in a normal life driving, you do not have these board games, right? You have continuous information, like vehicle is 1 meter ahead or 1.1 meter ahead or 1.2 meter ahead, this kind of information. So with that, you need to have a more generalized, you have a continuous inputs, observation space, basically, not discrete observation space like a chess game or a board game. Sometimes you have discrete, continuous action space also. Like so, for that, deep Q learning basically came where it kind of came up with neural network approximator for the Q table we just mentioned here, and then with that you can kind of approximate all these different state action pairs. Again, like a lot of, I think this is too much details, but the main thing is like DQN took a tidy game and given up, pixels basically, and then it broken down that into, your normal neural network problem. And then with that, it married basically the the normal network problem with reinforcement learning infrastructure, which basically is trial and error many times with, again, it needs to go into more details, but some kind of trial and error with your environment, and then optimize that neural network via backpropagation and come up with a good policy. So a lot of different style of algorithms, but most high level, there is model free algorithms, which is what we are kind of describing and which are more used right now, which are the neural network based algorithms. Then the model based algorithms are kind of where you have some idea about, some or full idea about your models, like a board game or a chess game, where you know what the rules are. But even if you know the rules, it's kind of hard to know what would be the optimal strategy to play the game. So RL has a lot of framework basically. So like I mentioned, you have, if we go with the model free algorithm, which is neural network based, you have to have, like, my point is not to kind of throw everything here at you guys, but it's more to kind of focus, how many pieces of the puzzle are there for doing a reinforcement, like reinforcement learning. And by doing reinforcement learning, you'll probably learn a lot of different things that you will get. You can transfer that domain knowledge in other areas as well. So you have to learn about simulation first of all to create an environment. That's what I mentioned here. You have Unreal Engine simulators. You have environment model wrappers, basically, where it abstract. It's like an API, basically, that you will interact with. And the reason of the API is basically it wants to have the solutions that the reinforcement learning give very abstract, and have the same interface, basically different. What end up happening is you get a lot of off the shelf algorithms from OpenAI or other platforms, basically, that you can plug and play when you're starting, instead of trying your own algorithms. And of course you can come up with your own neural network algorithms, but that is a different thing. And then you try to train the algorithms first with in your laptop, and then you'll have to scale up to basically some cloud-based computing platform like AWS or GCP. You need to when you go there, if you're working with a third-party provider, you'll have to deploy container-based solutions like Kubernetes or Docker, basically. That's what I've kind of mentioned here. So there's a lot of pieces of the puzzle. So again, like a lot of different things. I try to not go too much detail, but the reinforcement learning is very broad topic, so we cannot cover everything here. Actually, for the sake of time, I probably want to skip this, but there are, multi-agent, multiplayer, self-play, different kind of next steps, basically beyond the first step, where you just learn how to do the basic algorithm of basic DQN in this structure, basically, where you can learn with many other participants who are also maybe trained with reinforcement learning agents. It's a pretty evolving area. Putting this in the context of autonomous vehicles is basically, usually, you try to do this kind of things, like I mentioned, for each different kind of scenarios, basically, like highway or intersection, create a state and observation space of your closest in vehicles. You define, the problem, basically, what you're trying to solve. Constraint problems, you can use like a action space, for your action space could be just, lane keep or lane change. For a lower level, for unconstrained problem, like which I show here in the left hand side for traffic, for parking lot, you might want to come up with the steering and angle and excellent brake pedal torque, which so use this continuous action space. Basically, you use the discrete space or continuous space based on your problem. Then you can deploy your agent that you train in simulation, like this kind of environment, to a real world problem in the real car. Basically, you can have multi-agent, multi-goal problems, many more sophistication layers which we don't need to mention here. And more importantly, you need to have a level of safety. The RL policy usually will be, it's a offline optimization scheme. So you'll still have to have some kind of online algorithm, which your conventional algorithm has to go in conjunction with a RL-based algorithm. Again, like I'm trying to summarize what are the benefits of behavior with DRL. Basically, it can, because you are using a neural network, it can generalize much easier for the planner to new situations, like humans can. Like you can, if you're given new situation, you can adapt to a new situation. Obviously, smaller code space, you are not writing for each different kind of problems, this situation versus that situation, that you handwrite in code. The optimizations is all, the training and learning are all offline, and in online is just a prediction problem. So it's much faster online. You can combine search and the spatial and temporal search basically together in the reinforcement learning, which is very difficult to do in a cost-effective manner for any planner to today. With the conventional planners, you can also benefit from the state-of-the-art model algorithms. Everyone is the researchers are coming up with. You can also benefit with the state-of-the-art deep neural network algorithms. Yeah. Also, this involves a lot of simulation effort. So there's a symbiotic effort that goes on with your simulation team, basically, because most of the training you will do in simulators, you'll have to, those simulation engines can then be used to conventional planning also. The drawbacks are, of course, the black box decision making. For safety purpose, the RL today cannot just be used or deployed alone. You have to have a conventional motion planning algorithms, which we described before, motion or behavior planning algorithm together. Most of the state-of-the-art algorithms are policy based. I'm not going into that. Actually, I didn't mention policy and value algorithms. There's a tendency of the policy-based algorithm to get stuck at local minima. That's the problem. And RL is need a lot of infrastructure building, and RL is still a little bit of a kind of still in between research and deployment phase. With that, I'll try to mention what are the typical job roles that you will find in this domain. Higher level, you will find software architects. And these are probably possible in, present in any domain, not in this domain specifically, but architect's role would be to construct the architecture, which I kind of gave you in the planning architecture, and even more into some more details of like what is a motion planning architecture, what is a behavior planning architecture, what is a controls architecture, like that. A systems engineer would be involved with the hardware aspects and safety aspects. Obviously, like any place, you'll have program and product manager. More domain specific areas, you'll the planning and controls are really software specific. Even if you look at, especially planning, when you go to perception, you deal with hardware. When you perhaps go with controls, also you deal with hardware. Where you work with planning, be it behavior, motion, or whatever other planning you're doing, route planning, they're all software specific. So most of the job would be software related here. So you'll have motion planning algorithm engineer, behavior and route planning algorithm engineer. You have prediction algorithm engineer, motion prediction. You have vehicle control algorithm engineer. I've tried to mention what kind of, mentioning them again, what kind of algorithms typically you'll have to learn for these kind of areas. That kind of gives you an idea about What are these? Like, for example, motion prediction, you might need more statistical background, whereas behavior and route planning, you'll more need data structure and graph search background. One added benefit is like most of the planning and controls domain can be taken to any other robotics domain and directly transferable to any other robotics industry domain, and you can work in there as well. How to get into this domain? Again, there's some things which are probably common between this domain and any other high tech domains. So the minimum requirement would be at least to have, it's a competitive domain, so companies are looking for at least bachelor's or equivalent in relevant field: computer science, electrical, mechanical, software, automotive. The more the better, the more the merrier. You internship or academic personal projects, you need to always kind of make yourself different from the rest of the pack. The preferred requirements, obviously not everyone has this, and masters and PhD in specific domains. Like if you're going to reinforcement learning, maybe you'll have to either have advanced degrees on those fields, or some specialized online courses beyond the starter courses to show your expertise in those areas. Job experiences in these areas are, of course, any motion planning or controls domain would be also very good. And then you have to standing out from the pack. Like you have to not only like you have to be maybe working a specific competitor. Then it would be if you are working for Baidu, then you can Baidu Apollo. Then it would be easier for you to make a switch to Waymo or Cruise, for example, and that kind of thing. You have to work on participate in online competition. But for motion planning and controls, a lot of stuff are not possible online. So you'll have to perhaps get involved in local robotics competitions. This is important, highlight your personal coding projects in GitHub, which should also, include regular commits, kind of show that you are not trying to suddenly show some of the, to basically show that you are really interested in software, not to get a job, basically. Just you are always regularly working in that. Practice software programming skills with online websites like LateCode or G2G, GFG, basically. And so obviously research any particular company if you are interested in like Waymo or anyone. Then